Good morning, everyone. My name is Andreea Dumitrașcu. I'm part of the Connect University team, and I'm delighted to welcome all of you to another interesting session of the Connect University Summer School 2021. As a quick overview on the Connect University, the project is the knowledge sharing flagship of DG Connect, aiming to promote digital policies to society at large. This is the sixth edition of summer school that we are organizing, and it is focused on digital for our planet. All the sessions are recorded and can be reviewed afterwards, either directly on the Digital EU YouTube channel or on the Connect University webpage. Some other great sessions are still in the program this afternoon and tomorrow. The link is published on Slido, and also don't forget about the certificates that you can get if you attend more than 7 lectures. For today's session on EU Copernicus program acting on climate change, we invite all of you to join us on Slido using the code Copernicus. I repeat, the code for Slido is Copernicus. You can comment and ask us questions, and we will allocate them accordingly to our distinguished speakers of today. Also, please use the hashtag ConnectUniversity, one word, when sharing insights on the event on social media channels. Without further ado, I'm pleased to welcome our moderator of today, Mr. Eric Anderson from DG DEFIS European Commission.
Good morning. Good morning, everyone, and thank you for this opportunity, and thanks for dedicating a session to Earth observations and climate change. My name is Eric Anderson, and I work for DG DEFIS, one of the Directorate Generals of the European Commission that is devoted to defense industry and space. So I'm on the space part of the European Commission. I will be the moderator for the session. We have three excellent speakers lined up, and between each talk there will be a few moments for questions from participants, and after all the talks have been completed, there will be a general question and answer session as well that I will try to moderate. So I will start the session by introducing to you the Copernicus program, a kind of an overview of the Earth observation program of the European Commission. The program consists of a space component. So the European Space Agency provides and launches and operates satellites on behalf of the European Commission to collect relevant Earth observations for the use of services. So the second component of Copernicus is a set of services that deliver higher level products and information to users. And all the data that we produce is associated with an open data policy. So this is basically what I just said. So on this slide, we see to the top left a representation of the group of satellites that European Space Agency operates on behalf of the Commission, and they are called the Sentinels. There are 6 of them, six different series of Sentinels, and I'll come back to what those are in a moment. The middle part of this panel shows the services, and there are also 6 services, and I'll come back also to those. And they, of course, use the data that we collect from the satellites, as well as data from other sources, in particular, other satellite data sources, and in situ observations taken on ground, or in some cases in the ocean and in the atmosphere. And all this information is combined within the services to produce added value products for users. The various parts are operated with different organizations that we are in partnership with. In the center there, you see at the top, the European Union member countries. You see the services are operated by expert agencies. You will hear from ECNWF in the following on talk that operate 2 of the services. On the right, you see the in situ part is coordinated by the European Environment Agency. And on the left, you have the European Space Agency, ESA, and EUMETSAT. And you have the various agencies that operate the contributing missions. So here are the Sentinels. There are, as I said, more than 6 satellites. There are 6 series of satellites, and how many there are of each you can see in the table here. In some cases, 2 satellites are already in orbit. In some cases, the first satellite in the series is still to be launched in 2022. And each of these series of satellites are dedicated to providing observations on a particular aspect of the Earth system, be it atmosphere, ocean, or snow and ice, with a different instrumentation on board each of those. The details are on the slide. When it comes to the, so all the Sentinels are fully funded by the European Commission. These, what we call contributing missions, are also very important because they are existing in the environment in which we operate. So many of them are European in that they originate from Europe, but also international cooperation gives us access to additional important satellite information. And I think you will hear from some of that coordination in the final talk in this session by Anthony Ray. And if we're thinking about the sort of data handling challenges that are involved in this, they are very significant because of the very large volume, the large variety of data that we collect from these various types of satellites, and also the speed at which the collection and processing of the data has to be done. And therefore, this is becoming a very interesting area of exploitation of IT techniques, such as big data, artificial intelligence, and so on, to fully exploit the information content in the vast amounts of data. The services are doing a lot of that themselves. They combine the information and provide tailored products for various user groups. The services are climate change, which will be covered in the next speech, land monitoring, marine environment monitoring, emergency management, atmospheric monitoring, focusing on air quality and greenhouse gas concentration, and finally, security. The flow chart here from left to right shows the satellite and in situ data as input to the services in the center of the chart, delivering data to either end users or to what we call downstream services that exploit the data and can exploit it for commercial use. So the program itself is seen as an engine for economic growth in Europe. So we have therefore data sources from the satellites. We have the service information coming out of the services, and we have the value-added services and applications at the final step. And each of these steps, the evolution of each of these steps, is very steered towards users' requirements. So there is a comprehensive process by which the user's needs are found out, collected for determining the strategic, technical, and operational requirements and the evolution of those for the future of the program. And so here are some of the industries that are dependent on Earth's observation data and therefore are keen users of the Copernicus data, either in raw form or often from the services. You can see here important service areas such as energy, health, insurance, and so on, and increasingly also the state, the health of the ocean. The success of the program has been established partly through societal economic benefit studies, and it shows those sort of studies give us information about the economic activities built around the data that we provide, the number of companies that are using our data, the proportion of EU companies that exploit Copernicus services in Europe, and simply the number of users that are registered to the various data hubs that the services provide. So we've just completed the first 7-year period of the Copernicus services in general, and we are ramping up for starting the next 7-year period from 21 to 27. The funding is in place, the outline work programs are in place, and the first priority is simply to continue the success story that we have started in terms of, but there is also some opportunity to continue to improve. And these are the 4 areas: the data acquisition, the user services themselves, access and distribution to data, and promote further the user uptake. These are perhaps the focused areas for further improvement in the next period. When it comes to data collection and the policy areas that are will be our focus for the future, you have some of them here. The continued focus, of course, on climate and climate change and its impact all around the world, particularly on the Arctic, where we see increasing devastating impacts on ice and hydrology in terms of both flooding and drought. We will also work on emissions, determining emissions of greenhouse gases at greater detail and trying to pin those down to the exact sources from industry, agriculture, and the uptake by forests and ocean. And also food security is a key area to focus on for the next 7-year period. And we have found that although we have the 6 series of Sentinels, there's also room for improvement on the satellite side. So with ESA, 6 satellite concepts have been evaluated. They are mentioned here. 3 of them actually have a focus on monitoring in the Arctic, characteristics of the Arctic, sea ice, snow cover, also the ocean surface in the Arctic. One is dedicated to emissions of CO2, and you will hear from that from the ESA talk in a moment. And one is focused on high-resolution data from the land surface. So the most important, this is my final slide, the most important new element in terms of service will be the monitoring of anthropogenic sources of CO2 to really measure from space where the CO2 is emitted from countries, from cities, and from large point sources. So we will be able to monitor emissions from cities and industries, as indicated here. And also, the point of this is also to be able to determine with data that the various measures that people in countries are implemented to mitigate the greenhouse gas increase is actually happening, so that you can see that those mitigating actions have an impact in terms of greenhouse gas emissions. And that new service requires both an additional satellite series, which I said you will hear about in the talk from Isa, but also new service elements to process that data and produce specific outputs for users and policymakers. And that concludes my talk. If there are specific questions on this, then of course I would be very happy to answer those. I will see those coming up in the chat box in a moment. I can't see them right now. But not to lose any time, I would really like to now hand over to and introduce our next speaker. And our next speaker is Carlo Buontempo, who's the director of Copernicus Climate Change Service at ECMWF in the United Kingdom. So, Carlo, it's over to you.
Thank you, Eric. Thank you very much for the introduction. And I will be talking about the Climate Change Service, as you mentioned. Let me put it in full screen mode, the presentation. As you mentioned, Eric, in your introduction, the Climate Change Service is one of the 6 services that represent the service component of the Copernicus program. And 2 of those services that you see listed here, the Atmospheric Monitoring Service and the Climate Change Service, are managed and run on behalf of the Commission by the European Centre for Medium-Range Weather Forecast, which was based in Reading and will still be based in Reading in the future, but it also has now a leg in Bologna, where the supercomputer is, or soon will be, and in Bonn, where a significant part of the staff will relocate in the autumn. So the 2 services have different goals. The Atmospheric Monitoring Service, as the name says, provide consistent air quality information about air pollution and health, solar energy, and so on. So it's really about the trace gases and the aerosol in the atmosphere. While the Climate Change Service supports society by providing authoritative information about the past, the present, and future climate in Europe, but also in the rest of the world. The central piece of the architecture of the Climate Change Service is something we call the Climate Data Store, and is possibly a bit of a misname in the sense that it's not a store, because as Eric mentioned in his introduction, actually all the data is open and free. And it's not even a storage unit as such, because it's a distributed system or semi-distributed system, meaning that the data can be anywhere on the planet. The idea is to have a centralized and unique entry point to this wealth of data. And we became operational as a service in 2018, so we are quite junior with respect to other services. But over the course of the last 3 years, we managed to sum up some 90,000 users and counting. So the infrastructure is really designed to transform this petabyte of information that come from satellite, they come from station data, they come from model, into a few kilobytes of information that can be used by legislator, by business, and in some respect by citizen. You can find more about the Climate Data Store and the program as a whole at our URL that you find at the top of this slide, and it's cds.climate.copernicus.eu. But again, to attach once more to the talk of Eric, this is really big data. Satellite produce a huge amount of data. The processing of this satellite do as well. So we are talking in the petabyte, and this means having an appropriate infrastructure is essential if we want to, on one side, deliver this information, this data to the user, and on the other, process it and transform it. Okay. So what is it on the Climate Data Store? But there are observations. These are the bread and butter of all we do. These are satellite observation, as we were hearing before, but also ground-based and in-situ observation. Then there are the climate reanalysis, and I will say a bit more about those in a minute. But it's essentially our reconstruction of the past weather. Then there are the seasonal forecast, so outlook next 6 months, and the climate projections, which is an outlook until the end of the century. So one step at a time. Let's start from observation. We use the concept of GCOS, so the Global Climate Observing System, the concept of ECVES. ECVE stands for Essential Climate Variable, and is a set of 54 variables that are considered essential to characterize the climate of our planet. Of these 54 variables, the Climate Data Store gives access to 22 at the moment, and our plan is to actually increase the number into the mid-30s. So I'm talking about variables such as sea surface temperature, snow cover, or soil moisture, or temperature, and so on. So all this information as observational information is available on the Climate Data Store. The second tier, as I mentioned before, are the reanalysis. If you want a catchy way of explaining what a reanalysis is, you can call it a map without gap, in the sense that it provides while the observations are scattered and are in a specific location, a specific point, the reanalysis combine this information coming from observation into a numerical weather prediction model, so that information exists, that data exists any place in any place of the planet at any time. So these reanalyses go back as far as 1950 on the back end, and on the most recent end, they are in near real time, meaning that the most recent data set is 5 days old. But on top of this global reanalysis, that at the moment is at 30 kilometers, and we are planning to actually increase a bit the resolution in the next generation, there are a number of other products at higher resolution. So one is the ERA5 land. So ERA5 is the name of this reanalysis that goes back to 1981 and actually will be extended back to 1950 as the main reanalysis, but also European and Arctic reanalysis. We know that the Arctic is one of these hotspot actually for climate change. So we decided to put a specific effort in characterizing the climate of the Arctic with a pan-Arctic reanalysis that will be produced in the next few years. But also in Europe, clearly that's where we belong. We have a high resolution product based on a downscaling of the ERA5. And what this gives us the opportunity to monitor the climate on any place on the planet and see how it evolved. So this is a very rich plot. Maybe I won't have time to explain in full, but what you see in the vertical is a cross section of the atmosphere from the bottom, from the land surface to the uppermost part of the stratosphere, and the color indicate the trend in temperature. The horizontal axis is time, and you see that color are getting yellower and yellower as we get to 2020. This is really the climate signal in the making, and you see also the cooling of the stratosphere. This is possible because we can combine all this information coming from all over the planet in a single model. But especially if we go back in time, then it becomes essential to use every single piece of information we have coming from satellite. And in the early year, now we have plenty, thanks to initiatives such as Copernicus, and so we can really rely on those. But if you move at the beginning of the satellite era, then there are much fewer sensors. And in the pre-satellite era, there are, as the name suggests, there are really almost no satellites. So there are some specific missions. And we are trying to ingest and assimilate as much as possible, even of those early satellites, because the impact this satellite have on the quality of the reanalysis, on the ability to describe the weather and the climate in any place of the planet is actually very profound. The next data set I mentioned are the seasonal predictions. These effectively are a combination of seasonal prediction coming from a variety of models. So ECNWF model itself, but also the UK Met Office, Meteo France, CMCC in Italy, the Deutsche Wetterdienst in Germany, and also contribution from extra-European centers such as NCEP in the US, JMA in Japan, and ECCC in Canada. they're all combined together to give us an outlook of what the next 6 months may look like. And this is very important because a key element in our ability to adapt to climate change, it goes through our ability to adapt to climate variability. So knowing, for instance, that there will be an El Niño coming or a La Niña coming in the next 6 months may allow us to prepare and reduce the impact. Similarly, an effort has been put in studying the value added by decadal predictions. Those are predictions made for the next 10 years, not the next 6 months. And especially in Europe, there are some good case studies that shows added value of those predictions. Finally, there are the climate projections. Those are slightly different in the sense that the models are initialized and then run unconstrained by observation in many respects, but they are the bread and butter for climate impact studies. So the climate data store provide access to the simulation, they underpin the IPCC report, the CMIP 5 and now CMIP 6 simulation, but also high resolution simulation, the Cortex simulation, RCM, so regional climate model simulation for Europe and for a number of other domains all over the world. An effort has been put to make all this data look the same. So you can go on the catalog, browse the catalog, and find the entry that you're most interested in. And then if you look at the entry comes with a description. An effort has been put in make the description as plain and simple to read as possible, describing what the dataset is all about. And then through the web interface, it's possible to select the different parameters, different location, and retrieve the data. But an important element of that catalog entry is not just the description of the data, it's also the characterization of the quality. So an effort has been put in characterizing and scrutinizing all the data to ensure that is generally of very good quality. But more importantly, given that the quality somehow is in the eyes of the beholder, attach to each data set sufficient quality attribute to allow the user to make their own call on whether that specific data set is or not fit for their purpose. I was talking about the web interface. That's the most visible element, but the vast majority of our users actually retrieve the data through an API. So there is an API, it's well documented, and it can be used to retrieve any of the parameters, any of the variables that we have more efficiently directly in a machine learning way. We use all this information also to produce a number of visible output. Probably the most visible one is the European State of the Climate. This is typically published in spring, around April. So the last one was published towards the end of April, and look back at the year that has passed. So in this case, it was 2020. And is a really collective effort. So there were over 70 contributors from all over Europe and beyond that played a role in the report this year. And we use the observation, we use the model output, the Reanalysis output to depict accurate and detailed analysis of what the year has been. But it's not the only output visible output of the program. An effort has been put in attaching to the data set sufficient computing capability to process and develop application. So rather than browsing this petabyte of data, having a number of tools that allows to explore the little bit of information that people are interested in, and actually having a system that is sufficiently flexible and agile to allow others to develop their own application. So you can start with something as simple as a typical Hello World application where you plot a variable on the map, maybe the day of your birthday, what the weather was looking like. But you can do something much more complex as looking at sea level rise or impact on agriculture, impact on shipping or infrastructure, and so on and so forth. So all of this is happening, and there are plenty of case studies showing how the data is being transformed in all these applications. And we really see ourselves as being one of the engines behind the adaptation to climate change in Europe. So for instance, on the Climate Adapt portal of the European Environment Agency. Now there is a European Climate Data Explorer that actually is based on the Climate Data Store and interfaces directly at a machine layer with the data on the Climate Data Store. But being operational is much more than giving timely access to good quality data. It means having a number of functions such as user support, training, quality control, and so on and so forth. And this is really what we do. We have an excellent user support team that is able to address the queries of our user efficiently when it's required. We have a bit of a private cloud that supports this application I was telling you about, and you can use it as you like, but it's more of, doesn't have the elasticity, doesn't have the ability to scale to support a commercial exploitation as such. For these, there are new initiatives that are coming along that are much better positioned. Now, I'm just getting towards the end, but I thought, given that I'm talking at Connect University, to highlight some of the point of contact between Copernicus Climate Change Service, especially, and Destination Earth, which is the new kid on the block and is an extremely exciting program. Well, the two first things to say is that the two initiatives are not the same; they are different. But there is clearly an intersection that is significant between the two. And the union of the two is more than the two parts taken apart. So this is the essence of the message here. So, well, let me actually skip to this one, because I think this is probably more important. So if you want, Destination Earth is really a visionary investment to push the technology our society need to deal with the climate change challenge, for instance, and is far-reaching and very innovative. While on the other hand, Copernicus and the Climate Change Service in particular is devoted to developing services and maintaining this large user base that we have. Also, Copernicus has a combination of modeling, exercise, and in situ and Earth observation data. So this merging of product that Eric was mentioning. And the focus is very much on service implementation rather than exploitation of science. So we really, given that the two programs have a number of common players, with EUMETSAT and ESA and ECNWF, it's clear that there will be synergy, and we want to ensure that this synergy are fully exploited. So let me just close with this slide, because we have one single planet, and we have a climate that is changing. And if you read the news and look at what's happening in Canada at the moment, I would say it's changing also alarmingly rapidly. And we have a set of policymakers for adaptation and mitigation that we want to inform and provide good quality to. And so we definitely need to work the best we can with all these new resources and new tools that different programs are providing to meet this requirement of the policymakers. Thank you very much for your attention.
Thank you so much, Carlo. That was excellent. I would like to encourage all the participants, please, to come forward with questions you might have for the most recent speaker. It may take a moment or two for those to appear on my screen. So in the meantime, I would like to ask you something, Carlo, if I may. You stressed that obviously with climate change, one of the ways to describe climate change is that normal weather is a thing of the past. And you already alluded to what's happening in Canada right at the moment. And there was a scientist on TV, BBC yesterday, who said that if we run simulations of normal weather for years and years and years, as weather used to be a few decades ago, what is now happening in Canada just doesn't appear in those simulations. And I thought that was a very powerful way of saying that the observations that we now have of climate in Canada, of weather in climate, is an outlier. And I was thinking that the kind of predictions that you were showing in seasonal forecasting is really necessary to be able to show to the world what the next what the weather's going to could be like in the next season. What's your thinking around that?
No, absolutely. You're absolutely right, and actually, this is the reason, well, for me, probably the most important reason why maybe even just 10 years ago, when talking about climate, we were still talking mostly to scientists, and we are no longer talking to scientists. We have now an audience that ranges from finance to insurance, from agriculture to transport and so on. And the reason for that is exactly what you say. The past is no longer a good proxy for what is going to come. So if you have to manage a risk, then it's not enough to look back at historical time series and say, well, I want to protect myself to the 1 in 1,000 years return period flood, because that return period will change with climate change, and we need to really put an effort in ensuring that better quality, better information is provided to these decision makers so they can adapt. And for me, one of the ways to do it is looking at this combination of observations, up-to-date observations from satellite and modeling infrastructure. So I think this morning in the WMO statement about what was happening in Canada, there is a scientist quoted saying that this is probably an event that was completely impossible so over 10,000 years return period, and now it's no longer impossible. Actually, we have seen this clustering with 2 record-breaking events, one after the other, in the same region. So I don't think it will be the end of it. Not even Environment Canada thinks that's the case. And we really need to use all the tools we have at our disposal to improve our ability to cope with those changes.
Thank you, Carlo. Yes, I can confirm that I can see questions in the chat box that's in front of me. So thank you very much for that. So some of them are of general, very interesting, of a general nature that I think are very suitable for the discussion part that we will have towards the end of this session. But there's one, it's a little bit political, Carlo, but I'm sure you can deal with this one. It's what are the changes to UK access to services under the EU space program, given the Brexit situation? I mean, I can give part of the answer myself, which is that data itself is free and open, but you can elaborate on that, please, Carlo.
Yes, I see that the million-dollar question is passed to me. I mean, the reality is that we would like to see no changes whatsoever, because we have such a great relationship with our colleagues and friends in the UK. But we also need to respect the decision that they have made to leave the EU, and this has had consequences, if not else, because it made some of the negotiation of the contribution agreement between ourselves and the Commission more difficult in elaborating on what are the extra clauses that needs to be factored in. We haven't yet signed the agreement, but now is imminent, the signature. And my understanding, and Eric, you can confirm that, is that with the current agreement, it will be possible for UK entity to interact and be part of the program, because there is an intention for the UK to chip in, so to speak, into the Copernicus program. But that's as far as I know.
Yeah, thank you, Carlo. Yeah, that's right. There's a possibility for the UK to remain a partner or associate member of Copernicus, and those details are being ironed out. But the important point is that the data is free and open, and that's free and open globally to all categories of users, commercial, research, in all countries, including the UK. So that specific aspect does not change. Here's another one for you, Carlo. It's the pixel size of the program of products and data.
Yeah, well, I guess this is less political to answer. Well, there is no single answer to this because it depends significantly on the data set you're looking at. So you can go for, I was mentioning some of the resolution of some of the data set. In some cases, it can be as high as kilometer to kilometer. For most of the global product is actually quite a bit coarser. So Reanalysis is around 30 kilometers globally, and seasonal prediction actually is farther, even coarser. So it depends a bit. The aim is to provide the higher resolution that makes sense in terms of science, in terms of user requirement. So high resolution is typical, common user requirement. So we try to increase the resolution whenever appropriate and possible. But especially for modeling simulation, doubling the resolution means at least a factor 4, if not more, in increasing the expenses. So quite significant.
All right. Thanks once again, Carlo. And please stay online because we will need you for questions towards the end of the sessions as well. So there's one question on methane emissions, and I think we're going to leave that one until after the next talk, which will be on partly on CO2M, I believe. And the next speaker is Veronique Fernandez, who is a program manager at the European Space Agency. Over to you, Valerie.
Yes, good morning. Thank you, Eric, for leaving me the floor. Let me share the presentation, hoping that everyone sees it. Okay, so good morning, everyone. Valerie Fernandez, as Eric said, I'm the program manager of the CO2M mission in ESA. So we're here presenting a number of information. Sorry, you are not on the right page, if I understand well. Sorry. Where you would have an overview of a number of elements related to the mission itself. But before going to the mission, I think it would be important that you get some understanding about a number of elements, because it's not so easy to talk about what is a mission made of without talking about where is the CO2 located, how do you transform an observable that is a CO2 element in a technical requirement, and how then you make it detectable from space. So this presentation will try to cover all of that, and from the chat, I think it should reply also a number of the questions. So let's start with a small video that is an easy one, but is there at least to give you some understanding of what the CO2 is. CO2 is in fact everywhere and covering the globe everywhere. And it's in fact quite a different type of source that is making CO2. You have what we call the biogenic source, so the natural one, where in daytime it's let's say made by photosynthesis, and it's in fact absorbing, so it makes the thing blue in this map, whereas at the night you have the inverted situation where it becomes red. But this is combined with another part, which is the anthropogenic source made by the people and human, where it's in fact increasing a number by emission during the day. So what we are after is in fact to understand this concentration of CO2, and the technical naming is the column mean dry mole fraction, but in the presentation I will call it XCO2 to ease a bit the naming convention. So if we are looking at this a bit more precisely, it means that we need to have some understanding at region level, so at more global level, but also understand the CO2 at country and at local level. And this means that you need to understand the atmospheric CO2 and CH4 fluxes at a certain interval to monitor the trend, if you wanted to have it in a global way, or you will have as well to understand the separation. And for this, you need to be at a more precise scale, which is medium-sized country, region, smaller country level, But on top, if you really need to make the understanding on what is coming from human, you have to go at a more local area, what we call the point source level. And here, this is where the challenge is here, because you will always have to mix the regional, the continental fluxes and budgets with the small fraction that is coming from the local area emitted by human. Then, of course, this graph is something that everyone should know, because no long speech to understand that we have an increase of CO2 and CH4 concentration that has started from the, let's say, 19th century, would say, but it has really increased a lot in the last centuries. Century, sorry. And here, in fact, the difficulty is really to make sure that now we are taking urgent measures, since there are the need to make it if we want to limit the global warming. The last agreement that has been taken at political level in that direction was the Paris Agreement, but it was one of the last. It has started already much earlier in the 90s, where a first convention for the climate has completely put in place the need for making some regulation and at least some move on the decision making, on the policy and on the decision maker level, to assure that we could control this. As I said just before, we need to discriminate two things: the CO2 from a background to a CO2 that is emitted. So what are the parameters that are playing in that sense? Is in fact the source. Yeah, is it a city? Is it a plant? Is it an area well densified by human activities or not? You need as well to have an understanding on the wind speed, because you have some turbulences created by the background that will mix up the direct emission. So what does it mean exactly? This is, at the end, what we want to measure is a small fraction among a large fluctuation. We can take the example of the water. Yeah, it's an easy example. If you look at the ocean, we are after the ripples of the ocean when you have large waves. So observing the ocean looks rather easy. It's now, if you want to detect the ripple, it becomes a challenge. But if you want to have on top a quantification of the emission from this ripple, it's a major difficulty, because it's what we are after. CO2 or element that is a fraction of what is in the atmosphere. But if you want to measure this by extracting the part from the biogenic fluctuation, we are after 0.5 ppm versus the 400 million. So it's 0.125% that is very challenging to get, knowing that when you look at a city like it is on the left side, it's about 1 ppm emission, and a power plant 2 ppm emission. So looking at the fluctuation is definitely what makes the difficulty in assessing the anthropogenic part. When we are looking, so that was for the CO2. The CH4 is in the same, it's the same situation. The difference is the amount you have in the atmosphere and the lifetime it has in the atmosphere. So it's something that is staying less long in the overall atmosphere, but it has one major advantage: is the biogenic fluxes are stable. So it means that if you have difficulty to detect because it's less important, you can still get it because of the fluctuation that are much less influencing the retrieval. So what counts, in fact, in the CH4 is to make sure that you have a right footprint for making this evaluation good. And what you see is on the left, what has been produced with one of the Sentinel, which is a Sentinel 5P, in which you are able to retrieve 90 parts per billion over a 40 square kilometer. And this is a type of anomaly you see on the left side. But when you are looking at other way of measuring, like OCO, you would be able to increase the understanding of the anomalies thanks to an increased accuracy. So here there is definitely a need not to only have a precision, but as well to have a location that is more precise. What I was saying when we were looking at where is located the emission, there was also a notion of influence from the atmosphere in the turbulence of the atmosphere. For making a better understanding of that, there is some possibilities by a tracer that is an NO2, the NO2, because the NO2 is exactly one of these gas that have the ability to stay in the atmosphere sufficiently long to have a possibility to trace it over a certain period of time. And when we are making an interposition with the CO2, you realize that it's not far away, because the NO2 source are located close to the power plant, you are able to also connect this to the CO2. So there is a good influence of the wind retrieval from NO2 to CO2. So you see that emission, like the one we are after, needs to combine all this information if you want to make it effective. And it's this observable that now that has to be transferred in the requirement. So it was already presented by Eric at the beginning. Here, there was some let's say ideas that were collected by the Commission via a lot of incentive and inventories of information that were made with the users, and all of this information have shown their necessity to make an overall system that should collaborate. It will not be only space, it will not be only ground, but this is all that is necessary to make a good monitoring and a verification system. And this capacity, in fact, have been put in place by a number of requirements or recommendation in two documents, the CO2 blue and red books, they are named like that. And in these documents, you have 4 pillars that are considered: the detection of emitting the hotspot over like the mega cities and power plant, the monitoring of this hotspot emission, yes, to make sure that we can assess the increase and reduction of over an area, an assessment of the changes, and for this you need to have a repeatability, and then have an inventory over a long time period. So this, in fact, if you translate with the information that the CO2 emission will do, it requires a high precision CO2 data with a high spatial resolution and no local bias, a quantification of the emission including the plumes at a revisit that is high, no regional bias with a separation between the biogenic and anthropogenic fluxes, and then have during this period of long estimate via the global stocktake to evaluate the drift, that is the long term and the short term, that could also in fact influence the decision that could be taken by the one who will have signed the Paris Agreement, for example. So who are the contributors? Today, it's not like we are starting with nothing. There is a number of contributing missions to this, but if you look at it, they are not in fact covering all what I was presenting as observable. So what we need is to have large-scale flux that is sampling at the right level. So you see that you have a number of missions that are with the correct sampling, but you need as well to have the local fluxes with a dense mesh. So here, there starts to be the problem, because most of the missions that have been put in place are able to make a mesh, but either the mesh is with a grid that is too coarse or is without the right revisit. Whereas in general, the spatial resolution of each samples is good. So the parameters that will play a role when determining emission would be the precision per spatial sample, the coverage and the revisit, the cloud contamination. I will come back on that because it's for sure an influence, the homogeneity, and the structure that you can resolve per effective signal. Okay. So if we talk about cloud, Yeah. Now, this mission, as I said, a number of them are there. CO2M will combine all of them. And what is important is to keep in mind that why we are asking for spatial resolution that is benefiting the local scale, it's also important to, in fact, remove cloud. The higher resolution you have, the better you would be in having sample without cloud. And this is an example that is taken with a number of instruments. CO2M is really putting the spatial resolution low to assure that you would have fraction of cloud-free measurement increased. That will then play an important role to get regular information and precise monitoring. Sorry, I've forgotten another thing, but to do that, as I said, you need a frequency. So the large swath needs to be there because you need to, at the same time of being very local, having the variability over the country. That's the pending, which is the local scale. Why local scale? Exactly for the reason of being able to look at the difference between a megacity and a power plant. If you look here on the right side, you see the blue points and red points. Sorry, black point and blue point. The black point being the city, yeah, with a very small fraction of emission that is seen, whereas you have much larger emission over the power plants. But if you want to make a good discrimination and have assurance that you are monitoring correctly what is happening over the power plant, you need a really good grid with a high resolution. So the high resolution indeed is coming from the users and the service makers that was thinking about it. And for CO2M, the decision was to be 2 by 2, which is already half of what it is used in the general trend for making services. Now, quantifying CO2, the CO2, sorry, the famous column of average dry mole, because now I would like to move toward the instruments. So what you need to do is to make sure that you are able to measure this fraction. So these famous molecules. And for this, you need, in fact, to have the vertical column of the CO2, so that is contained over a column, and you have as well at the same time to determine why the O2 absorption from the atmosphere. Why are we doing that? Is because we want to have a sort of normalized situation that is made independent to the surface. Because indeed what is happening is if you are at high latitude or low latitude, your effect is a bit different and perturbated differently coming from the ground. So the fact that you normalize with the O2 makes the information more comparable and more stable. So when we talk about quantification, it means that we need to have CO2 and similarly have the O2 measured together. So then the light, and this is what is measured through the light. Each time we are measuring, you know that, you know or you don't know, but the light is in fact in physics translated in an information that is a spectral information that is covering from the UV to the infrared. And what we are after is to detect certain band in this spectrum, particularly the O2, the CH4 and the CO2. The difficulty is in fact, so if the O2 is probably one where you have an assumption that is not covered by any other source, the difficulty is the CH4 and the CO2 are merged. Yeah, so you need to have the assurance that you have enough spectral bands that is looked at to assure that where the CH4 is the more present is more detectable compared to the CO2. And for this, you have specific area that are detected by instrument in the near infrared or in a bit further infrared to make sure that you are concentrating your effort on the possibility to retrieve the right molecule. This is then translated, this information is then translated in what the scientist gives to ESA, in fact, to have some guideline for defining the instruments for making this measurement. So considering what was the difficulty in observing and considering the need of having a right precise over small area, it has been translated in this parameter, what we call an absolute radiometric accuracy, an effective radiometric error, a zero level offset. So there are quite a large number of parameters, but there are these elements that we can control and that are directly connected to the product, like the XCO2 or the XSH4. The same applies for the NO2, because as I said, you need to have the NO2 detected in the same way. And as we need to be with cloud-free fraction, we are also detecting the cloud with very dedicated band for this to get the low water cloud and the cirrus discriminated. And for this, the sampling is very small, so it's even 10 times lower than the sample you have for the CO2 and the NO2, because then you are able really to remove in the sample of the CO2 and NO2 the contributors that is making the information biased. The last one, where I didn't put too much effort in the presentation up to now, is the aerosols. The aerosols is also an element that is perturbating a lot the light path. So when you are looking at the light going back to the satellite, you are perturbated by the atmosphere, in which aerosols are highly present. So you need to try to correct as much as possible this light path from the aerosol. For this, the spatial sampling has been assessed to be a bit coarser than the one for the CO2 and NO2, but that is made over the full range of the dynamic, plus on top over a field of view that is encompassing the nadir view, but more than that, the 120 degrees from side to side. So you are able to evaluate the bipolarimetry, the effect of the aerosol on the product. And here is what is depicted is the fact that some areas like India and China, where the level are extremely high, would have an effect, a dramatic effect, if not removed, on the concentration, which is what is presented on the bottom part. If you are not having aerosol removal, you are getting much coarser bias retrieval, which means that you are not able to discriminate the anthropogenic part to the natural part. Now, to complete this, I'm now going in the satellite itself, but then what is translated in requirement is to be done by instruments. So instruments that are on board this mission are, in fact, will cover 4 types of observables: the CO2 and CH4, the NO2, the cloud, and the aerosol. On the CO2 and NO2 CH4, you need what we call a spectrometer to have the spectrum that is scanned over a very thin spectral resolution by a grating. You need to have detectors that are extremely high sensitive, because you're looking at small size sampling. And on top, you need to also produce data with low noise, so that you're not perturbated by the signal data conversion. That's what we do with a spectrometric measurement. And for the cloud, it's a bit different, because here what you don't need to have a fine sampling resolution of the spectral domain. You need to have bands that are correctly monitored and correctly located. So here the spectral bands are larger. It's a stripe filter still, but it's not, you don't need a grating for that. You can do that with what we call stripe filters. You still need high sensitive detector, because we are going with a resolution which is 10 times smaller, and we still need low noise, because small spatial sampling means less signal, which translate in a necessary SNR that is still high with a low noise implication. And with this, we will be able to have the large HO2 absorption band retrieval. The principle of monitoring in polarimetry, here it's a bit more complex, so I will not enter in the detail, but what is important to keep in mind is you need to have systematically an information that is not covering only one direction, but be multi-angular direction at the same time of a sampling that the CO2 is done. So we need an instrument that is with a number of cameras that allows to go from this 120 degrees, covering the visible to the near infrared, like where the CO2 and NO2 is, because this is the place where aerosols are. And with this way of doing, you would be able to, in fact, scan the atmosphere and not just limit the phenomenon that are at the bottom part or at the top part. The key feature of this mission then, as I was saying, you need a lot of high resolution, revisit, and certain moment of the day that needs to be looked at. So this is what is happening here. Each satellite will have what we call the local, this is a local time descending node at 11:30 and is flying at an altitude of about 700 kilometers. Is covering the full Earth in 11 days. So it means that if you want to have a higher revisit, you need to increase the number of satellites. The baseline currently is with 2 satellites that allows to be at equator with 5-day revisit. But we should not forget that when we are talking about the northern latitude, where you have most of the human made production of CO2, we have already a revisit of 3 days. A third satellite is in also idea to be added. If it comes, it will be 2 days, between 2 and 3 days. Each satellite is designed like Copernicus needs, so it's 7.5 years. With an extendable of the consumable to 12 years, which makes the mission overlapping compared to the program development as it was presented by Eric. It's 7-year period, but here we are extended to make sure that we can cover more than 1.5 overlaps. And the category of this satellite is compatible with Legacy. So what is important to keep in mind is this development is made so that we would be able, let's make it happening with industry, to have these 2 satellites ready by end of 2025 with operational product in the year of 2026-2027, so that the global stock take would be enhanced with the data of CO2. There is a second, there is also another capability that is embarked and that is not so much talk so far, which is the sun glint view. Some areas which have a low reflectivity in Nadir are helping for getting more information when you have low reflectivity. So it's important not to just limit the path with viewing only on Nadir view, but have also the possibility to depict your satellite so that you can have the Nadir and the sun glint view that allows to then enhance the monitoring over certain surface which are highly reflective like snow. I give you just a brief snapshot of how looks the satellite. So it's a satellite that is, to make it quick, it cannot be fancy. So sorry, it's not the most creative way of making a satellite, but it's something that is made with all what is necessary to make this mission fast. With the electrical power, the system for controlling it, propulsion, the thermal end control and data storage that is sized for the need of this to cover all this observable in the time frame. And it's in fact made in a way that we call modular platform, which means that you have accommodation per panels so that you have less interdependency when you're making the integration and test. On the side of the payload, so the instruments, we said 4 observable, but in reality, it's 3 instruments because CO2, NO2, CH4 is in one spectrometer capability. So you have, in fact, a compact payload, and this is what is making this mission probably also different to what has been done in multi-instrument mission in the past. all the instruments are co-located. So it's like everything is made so that we are co-registrating the information as much as we can by design to avoid the inaccuracy you may have by the location. So that's very important. And by having the optical part co-located, you're also having a possibility to limit the thermal dissipation and the thermal disturbance of it. So, so you see that there is a big radiator on the edge, but this is really an important thing because it allows to have a thermal stability over the over the optical bench. Another element that is also helping
Valerie,
yes.
Valerie, can I ask you to move on to the conclusion when you can,
I'm at
please?
the end. I think it's the last one. One of the last. Yes. So the last thing is to say that we are going very close to make everything compact and co-located in an optical bench with minimization of impact by the environment. And as a conclusion, in fact, we are really at the end. It was to say that there is quite a large number of missions that are today planned to happen or already in space, yeah, that are concentrating on CO2 and CH4, but the capability combining all of them are not so many. And what counts is in fact that all of them will contribute to create synergies and complementarity. So at the end, and that's what is important to note, to make a mission like CO2M, you need to fill all these elements that I will not repeat from what I have presented, but they are necessary if you want to reach the discrimination of the anthropogenic source to the biogenic source. And I thank you for your attention.
Thank you so much, Valerie. That was really fascinating.
It's heavy. I'm sorry. It was an heavy one, but difficult to present a satellite without the context of the measurement.
That's great. Yeah, you really gave us the impression that although the Sentinels are operational satellites, there's a lot of high-end technology and innovation involved in each one of them. And I know for sure for the CO2M that it's unique in its ambition. So we're very excited to see what it will be able to deliver. So there are questions directly for you based on your talk. One is simply, what's the next big space missions at ESA? Of course, you know, you might want to say CO2M, but I'm guessing that the person asking is looking across all of ESA's space programs.
So, in fact, ESA is indeed not limited to the cooperation with the Commission, where CO2 and all the Sentinels are captured under Copernicus program. You have also all what is exoplanets. So I'm not the most relevant person to answer that, but missions are currently going to Mars or going to Europe, one satellite of exoplanet far away to retrieve different elements. There are missions related to the deep space deep space in a sense, looking at the background and try to get the better understanding of what the background impacts on the understanding of each planet. So there are quite a large number of missions. But the next to come, if I know my booklet well, is Mars. Yeah, the Mars mission is coming as the next one and should be launched in, if it's not, I think it's next year, if I remember well.
Right, and also a quick one. What is the error bar on CO2? I'm sure you had this in the talk of the CO2 concentration in a 4x4 kilometer resolution. So what's the error bar in the product?
Alors this, I have to say that's the mission requirement that is telling it. So this, we translate it in a radiometric accuracy and in a bias. So I hope that this is what the people is after, but we have a 3% accuracy. And we have an error of each measurement of 0.1%. So I don't know if it's in the final product that we are after, or if we are at the measurement that we are doing on board. But what is important is all of that is to make sure that we are reaching the 0.5 ppm that is necessary to achieve the discrimination between what is coming from the biogenic part to the anthropogenic part, which is in general an element of 1 ppm or 2 ppm if we talk about power plants.
Thanks.
Generation.
And that's a hugely ambitious target, and it's also the unique, truly unique capability of this satellite. Thank you again, Valerie, and as before, please stay online because we have a few more questions lined up for all of you in the panel at the end. So now it's my pleasure to introduce Dr. Anthony Ray. He's the director of the infrastructure department at WMO. And WMO is the World Meteorological Organization. It's the United Nations agency concerned with weather, climate, and water. So over to you, Anthony.
Thank you, Eric, and thanks to the previous presenters as well for a fantastic couple of presentations. So what I want to talk to you about today, it won't be a deeply technical presentation. I want to talk a little bit about the meteorological value chain, this kind of global weather machine that's coordinated in some way by WMO, and then what's the role really of WMO in this, and in particular in the coordination of global observing programs. So there's a kind of truism in meteorology and climate that weather and climate know no boundaries. You know, we know that the atmosphere has no horizontal boundaries, and you know, if we try to model just a portion of the atmosphere, this doesn't work very well. So everything that we do, whether it is a limited area model or whether it's downscaling, has to start from a global model. So even if we run a global model, the boundary conditions of that global model, if we run a regional model, the boundary conditions of that regional model will come from a global model. Similarly, if we want to do downscaling of climate predictions or whatever, that really needs to start with a global model, because the processes that drive the weather and climate are global processes. So I want to introduce this concept of the meteorological value chain. I'm sure it will be familiar to many of you, and there are many different ways to depict this. There's no right or wrong way. But we start with data collection and analysis, and that's really the focus of my talk today. Then we have some kind of modelling, global numerical weather prediction, global climate reanalysis, as mentioned by Carlo in his presentation earlier. Then we have post-processing and maybe some kind of automatic production of products, forecast interpretation and decision, dissemination of products and services to users, and finally, where we actually extract the value is the understanding and the use of the forecasts. So, you know, where the forecasts are disseminated and where the information is used is where the socioeconomic benefits are generated, and this is generally done at a national level by the NMHS, which is the kind of acronym that we use for the National Meteorological Hydrological Service. But WMO has a coordinating role, and I'll talk a little bit about these acronyms, WIGOS and WIS, later. WMO has a coordinating role, and both of these activities, as the data collection and analysis and the modelling, as I mentioned earlier, these need to be done globally. And so we have this kind of basic WMO infrastructure, which underpins all of the service delivery by the NMHSs, and this can only be implemented globally. And as I mentioned, the observation part needs to be done globally. So what have we done about this? In 1963, which is almost 60 years ago, the World Weather Watch was established, and the primary purpose was to ensure that WMO members get the meteorological information that they need to support their operational work and their research. So there were three elements of that: the Global Observing System, the GOS, the Global Telecommunications System, the GTS, which is really a network of wires and protocols for exchanging data, and the GDPS, the Global Data Processing System, which encompasses that modeling component. So as I said, this is nearly 60 years ago now. So how successful have we been? This is a chart, one of my favorite charts from Peter Bauer at ECMWF, and what it shows is the improvements in forecasts since the start of the 1980s. There's so much information on this chart that I don't know where to start really, but the blue at the top is the 3-day forecast, and then you've got the 5-day below that, the 7-day, and then the 10-day below that. And what you can see is there's a few trends here. Obviously, forecasts have got a lot better since the early 80s, but also we have the dark line at the top and the lighter line at the bottom. And what this is the difference between the accuracy of the forecast in the north and the southern hemisphere. And what you can see is that since about the early 2000s, the gap has closed. So we've got the same models running in the northern and the southern hemispheres. They used to perform not as well in the southern hemisphere. Now they're the same, and this is largely due to the increase in the availability of satellite observations. What you can also see is that let's say the 5-day forecasts now are about as good as the 3-day forecasts were maybe 10, 20 years ago. So there's been a very big and pronounced increase in the accuracy of numerical weather prediction, and what that's meant is that the dependency on NWP by the National Met Services has increased to a point where it underpins the vast majority of the services that are delivered. So when we talk about global NWP, we've got an estimate from a recent World Bank paper. It's estimated that numerical weather prediction might enable around 132 billion of worldwide economic benefits through weather prediction. So as I mentioned, this underpins modern weather and climate services at all spatial and temporal scales. And you might ask why this talk's supposed to be about observations. Why am I talking about NWP? Well, NWP provides the requirements for the global observing systems, and the systems that I mentioned earlier can only be tackled at the global level. So if we look, this is a little bit of an older example. It's from Australia, from my home country, but it depicts in a number of panels just a snapshot of the observations going into a global numerical weather prediction model. And there's a couple of things that you can take from this. One is that the satellite data predominates, and where you can see the broad swaths of observations, these are clearly from polar orbiting satellites. There's also in the top right some data from geostationary satellites, and then there's a couple of panels at the top left and the bottom right that show in situ observations. So there's a huge amount of data that's required to drive these models. More than 20 different satellites, a globally coordinated program of surface-based observations. So that's really what I wanted to talk about, WMO's role in doing that. So I talked about satellites. It's important. Satellites have been a massive driver of improvement in meteorological services and in the accuracy of global numerical weather prediction. Is a snapshot. Once again, this is probably from a few years ago, but it just demonstrates the kind of ring of geostationary satellites that are used, plus the polar orbiting satellites operated by the US, by China, and by EUMETSAT, which provide this kind of backbone of numerical weather prediction. I talked a little bit about the differences between the northern and southern hemispheres, and I think this is a snapshot of surface-based observations just from a point in time. What you can see is that there are many observations in the northern hemisphere, and in the southern hemisphere, where of course there's much more ocean, there are less observations. You can also see that there are some parts of the world, Africa, for example, and parts of South America, where we're not getting very many surface-based observations at all, and this is a separate issue that we are addressing separately. It really requires capacity development and capability development in those countries. But there's a large program of observations that are coordinated by WMO, both basic kind of automatic weather stations, plus a program of upper air weather balloon soundings that all this data is exchanged in real time and provided to the numerical weather prediction centres to run their models. So it's a lot to do. So how has the kind of the World Weather Watch that I mentioned earlier, how's that evolved in the 60 years? So the GOS, the Global Observing System, has expanded into the WIGOS, the WMO Integrated Global Observing System, and this integrates much more than just the basic kind of weather observations that I mentioned before. It covers atmosphere, land, oceans, and the cryosphere. Similarly, the GTS has evolved into the WIS, the WMO Information System, which is has the goal of providing open access to environmental data, discovery and access to authoritative weather, water and climate data. And then the GPFS has evolved into something called the seamless GDPFS, the Global Data Processing and Forecasting System, which encompasses the kind of global numerical weather prediction centres at the top, but there's a cascading kind of process of providing products right down to the least capable members of the WMO family. So this talks partially about frameworks. So I already mentioned WIGOS, and I'll talk a little bit about that on the next slide. WIGOS is a network of networks in the sense it encompasses the GOS that I mentioned earlier. It encompasses the WMO hydrological observation system and observing components of the Global Atmosphere Watch and of the Global Cryosphere Watch. But it's not everything that we need, and particularly for climate, but even for weather, it does not provide everything that is needed when you take a Earth systems approach. So WMO participates very actively in a couple of co-sponsored programs. One, and I'll talk about this one as well today, is the Global Climate Observing System, GCOS, which Carlo mentioned in his presentation. This is co-sponsored by WMO, but also the International Oceanographic Commission, United Nations Environment Programme, and the International Science Council, implemented by WMO. And then we have the GOOSE, the Global Ocean Observing System, which has the same co-sponsored, but which is implemented by the IOC of UNESCO. So what's WIGOS and what does it do? You know, for all of this data to be able to be used interoperably, we need standards. So WMO provides and sets through our network of experts the internationally accepted standards and best practices for observations and data compatibility. We support that through the use of standardized data representation and formats and metadata and so on. So WIGOS aims to improve the quality and the availability of data and metadata in order to develop capacity and improve accessibility. There's also an important dialogue. I talked about satellites before, and there's a very important dialogue between WMO and the satellite operators in terms of expressing the requirements for satellite observations to the satellite operators, both through the coordination group on meteorological satellites, the CGMS, which will have its 50th meeting next year, and the Committee on Earth Observation Satellites, CEOS. So that's WIGOS. I wanted to talk a little bit about GCOS as well, as both of those are GCOS is integrated to some extent within my department at WMO. So GCOS works toward a world where users have free access to the climate-related information that they need, and it does this by identifying user needs for climate monitoring around adaptation, sustainable development, and so on. It ensures that climate observations are enhanced and continued into the future, and it's recognised by the United Nations Framework Convention on Climate Change. So there's a status report and the implementation plan from GCOS that are tabled at the COP meetings, the United Nations Climate climate change conferences. So GCOS, it's a little bit different to WIGOS in that it doesn't go down into the specifics of how to take the observations and so on. But what it does is it has a regular cycle of review and planning. So it looks at where are we now in terms of the adequacy of essential climate variable observations. It develops an implementation plan, which is presented, as I mentioned, to the UNFCCC, which provides a kind of a overview of what action is required to address the observation gaps. And then we have a response from the observations operators. So that might be the National Meteorological and Hydrological Services, could equally be the space agencies or other networks and research organisations. So GCOS developed this concept of essential climate variables that Carlo mentioned in his presentation. These are physical, chemical or biological variables that contribute to the characterisation of the climate. They're not standalone, they're part of a broader concept, and they're founded on the climate science and the observational capability and infrastructure. And we have a large network of experts who support the development of the ECVES and the monitoring of the ECVES. And there's a few principles. It should be free and open, transparent, accurate, useful, timely and long-term, and based on the best available science. So we have a large number of ECVES across the hydrological cycle, across the carbon cycle, across the biosphere, and across the energy balance. So one of the things that you'll note about GCOS is that it is much broader than the kind of traditional remit of WMO. It's a co-sponsored program, and it has a reach beyond just the basic kind of weather and climate variables that WMO is, I guess, used to dealing with. The ECVES are broken up also by really three categories: land in orange, water and ocean in blue, and the atmosphere in light blue. So the ECVES kind of underpin, as I mentioned, the whole process of the status report and the implementation plan. One of the key things that I wanted to say, and I hope this has come through in my presentation, is that this is a global problem and it requires global coordination, and GCOS and WMO cooperate with a wide range of networks. So some of the ECVES, for example, in the ocean domain are the responsibility of GOOSE, the Global Ocean Observing System, and we have a strong linkage through our oceans physics panel between GOOSE and GCOS to provide those observations. But similarly, on the atmosphere side, the WMO networks provided by WIGOS provide the bulk of the contribution there, and under that I would also include the Global Atmosphere Watch and things like that. And then we have, as I mentioned, satellite observations coordinated by CEOS and CGMS. We have many other networks for terrestrial ECVES, and there's a wide range of partners who support GCOS, including Copernicus, who provide support both in terms of observations of ECVES, but also in terms of supporting the Secretariat. So I'll make some final remarks. The observations for weather and climate really require a global approach, and increasingly understanding the Earth system requires an integrated approach across multiple domains. We can't just look at the atmosphere or just look at the terrestrial or just look at the ocean. We need to look at the whole system and the processes that run across those systems. And partnerships are critical to the global coordination and the sharing and interoperability of observations. And I guess from a WMO perspective, we're working very hard to harmonise data sharing across our own networks, but also with networks like GCOS and GOOSE, really for the global good. And I will stop there. Thanks very much for your time. I'll hand back to you, Eric.
Thank you, Anthony. That's excellent. I think almost goes without saying that a program like Copernicus would not be possible, would not be conceivable without the many years and decades of work that has been done before under WMO coordination in all the areas that you touched upon: climate, weather, coordination of satellite programs, and in situ observations. And many of the observations that are collected and exchanged under WMO coordination are, of course, used throughout the Copernicus program. And I think you saw examples of that in Carlos' talk. There is a question directed to you, Anthony, and it is what someone's spotted, and you pointed them out, the various data gaps around the world. And the question here is, what does GCOS do? I suppose, what does also WMO do to combat those data gaps and seemingly the exclusion of those regions in Africa, South America, and Asia that are not covered by observations currently?
Yeah, thanks, Eric. It's a really good question, and it's probably something I would have touched on if I had time in my presentation. But it is an issue for GCOS in that it will appear in the status report, and it's clearly a gap. But the observations where I was pointing out the gaps are really the observations that are facilitated and coordinated by WMO. These are basic automatic weather stations. These are the launching of weather balloons, and so WMO we've been focused on this actually for the past couple of years. WMO has we've approved at our Executive Council a new data policy, and this is a kind of overarching framework which, on the one hand, provides for the free and open exchange, or maintains a free and open exchange of observational data, but also the free and open exchange of modelling data. And why that's important is that there's a quid pro quo. The WMO members, the individual Met services, make their observational data available to the global producing centres, and in return they get back the value from the global modelling centres. And so this is important. This is really part of that value chain that I was talking about. We've revised the kind of requirements for our members for what observations need to be taken, and so we've set out under this thing called the Global Basic Observing Network, GBON, a defined spatial resolution and temporal resolution of surface observations that need to be taken. But that's not enough, because it doesn't address the capability gap, the fact that many countries either don't have the capability or the resources to take these observations and exchange them. So we are working with a large number of development partners on something called the Systematic Observations Financing Facility, or SOF. And we had the second potential funders forum for that this week. And what we're aiming to do is to raise a lot of 200 million. We are looking to raise 200 million in the first instance to provide to least developed countries and small island developing states to establish or re-establish their observing infrastructure, but very importantly, through a monitoring process, the WIGOS data quality monitoring system, which is also supported by ECVES. If countries are successful and they take the observations and make them available to the global community, then there will be some kind of support, financial support for them to do that. And so we are working to develop the SOF, and it is a really important initiative of the WMO, and we're looking to announce the facility at the COP meeting in Glasgow in November. So thanks, it's a really great question.
Thanks, Anthony, for that clear answer. Associated with that are the various technology challenges that also influence the availability of data across the world and the exchange of data. And I think that's going to bring us now to the first question that we're going to address in the panel part of today's session. And we're going to move into a little bit more on the technology IT side of things. And I think this first question that came in through the Slido is a suitable one that I hope all of us will be able to contribute an answer to. It's about, we've heard a lot about combining space data and other sources of digital data, and this will require strengthening of data processing and the creation of advanced algorithms. So this is quite a general question, but I think it fits very well within the scope of the entire Connect University. So who would like to have a first step at answering that? Anthony, since you're online, do you want to start, or do you want to think about it for a moment?
Well, I can start, because I think in a couple of things that we've talked about, in terms of global numerical weather prediction and reanalysis, which is built on the same technology. I mean, this to me, it's a mature technology, and it's bringing together space technology, space observations, bringing together supercomputing, bringing together in many areas for the processing surface observations, bringing in cloud technology. So I think it's happening, right? I mean, this is happening. I think where we will see the introduction of technologies like artificial intelligence, machine learning, will be in taking the outputs of those systems and integrating them with other data that comes from outside of the meteorological and climate community to assist decision making. So you might be bring together a forecast or a warning on a heat wave with demographic data or health data to assist a local area in providing warnings or protecting their population. So I think this is kind of an area that's mature, but there are certainly some of the developing areas like AI and machine learning, as I mentioned, where they can probably be used at different parts of the value chain. Thanks.
Thanks, Anthony. I think we'll go to Carlo. Do you have examples already of what you would call machine learning, AI, other modern techniques that perhaps the question refers to?
Yeah, certainly we do use machine learning, and actually there is a person at ECNWF who is leading on machine learning and artificial intelligence to be sure that we keep on top of this. But for me is more, I mean, this is just one of the many tools that we have available, but there is an infrastructural element that needs to be tackled. So Anthony was referring to Reanalysis as a mature technology, and I completely. And we have the ERA5, the Reanalysis of ECNWF, that are in the range of 10 petabytes. 10 petabytes is a huge volume of data that cannot be easily processed if you don't have a dedicated infrastructure. And infrastructure means ways of running the artificial intelligence system on the fly. It means having sufficient connectivity to download. I mean, I was referring to in my slide to this 70 terabyte of data we download to user every day. You need to have that infrastructure in place, and you need to be able to support it and scale it up. Because if we look at what's coming next, the resolution of the model will go up, the spatial and temporal resolution will increase, the number of variables required will go up, the number of data, the volume of data coming from satellite will go up. So everything is going to get even more critical, and so being efficient in terms of extracting that information, so machine learning, using machine learning or artificial intelligence within the model themselves to make them faster, is certainly something we are also looking into, but it's also changing the entire infrastructure, moving more to cloud-based solution. I think is certainly part of the solution.
Thanks, Carlo. On ESA's side, you have the responsibility to make masses of satellite data available to citizens in general for all your programs, and particularly also for Copernicus. And many of the services that ESA feeds are real-time services within Copernicus and elsewhere, or close to real time. So it's not just the large volumes, but it's also the timeliness of data delivery.
Correct,
So,
correct.
Veronique,
So
what's your comment on that, please?
yeah,
Eric,
there
sorry.
are yes, thank you, Eric. It's a super interesting multi-dimension question, in fact, because in this discussion of data and notion that you have an amount of data to work with, one of the first steps that is today done for the future Copernicus, it's not done for CO2M, but it's done for SHIME. It's even embarking the intelligence, the artificial intelligence for cloud detection. So there is also this move to make the data even more sensitive to the need at the closest part, which is when it's generated. So this is also to make for the future this information more sensitive to the need. So that's one part. The other part is related to what you say. We are having this tendency to increase a lot the amount of data because the technology allows it. Simply, you have bigger memories on board, so you are able to make more data on board, and you can communicate fast with antennas. So there is this tendency to increase. But what we have also seen that is coming more and more, it's the fact that there is this algorithm on ground that are developed with more synergies between data that reduce the time. So, okay, it needs time to develop the right modeling and make it efficient. And that's something that will probably take a bit of time for CO2M. But there is this idea to create synergies from the data. And that's the reason why CO2M, for example, have a short latency to the ground with simultaneous data coming for CO2 and aerosol, for example. The idea would be to have the product that is already corrected with the right level before having the final step. So ECMWF is working a lot on that in trying to assure that the product that would be received would remain independent, the CO2, the NO2, the aerosol one, but as well produce a category with EUMETSAT of product that are enhanced by having a better accuracy by synergies and reduction of error and bias created by multi, let's say, dimensional algorithm. Now, for what concerns the data rate and the amount, it's in fact a change of architecture that is thought in ESA with a cloud approach, which is really making easier the enhancement for having data access in a more real time. So there was a lot of effort, and it's still ongoing, to transfer the infrastructure from a physical to a cloud approach. So this is also something. I'm not the expert in that part, but this is what my colleagues report me from Esrin, and it's also something that is the way to do for the future, and considering the amount of the future data that will come from this new 6 Copernicus mission.
Thank you. Thank you for that answer, Valerie. We're going to go on to another question that I found very interesting. It's a little bit ambiguous, but the fact that it's ambiguous makes it possible for each of you to turn the question the way you like. Which would be the most important measure to be taken to foster European space sector? So foster this sector, this can be interpreted in many ways. Are we talking about fostering technological innovation, or is it fostering sort of the knowledge that we derive from the space sector and the services that we build upon it? So it's a multifaceted question. Valerie, do you want to start?
I'm probably the less. I'm not the one closer to the users, but fostering for the future is from this perspective, make sure that the knowledge is enhanced. So the knowledge is, as you said, based on a technology that allows to make it, but as well with the right way of interpreting it. So you need the dimension of making possible having this data, but on the other side, for sure, you would need as well the right way for using this data and disseminating this data to the person who would need to make it. So all in all is to find the good balance between how to push the technology on one side for making this happen, and have in parallel the right policy that push the people to be on the element that not just the scientists and the users of this data, but as well a transfer for making clear that all of that is for the help of the community. So you need as well the transfer in a policy way for considering that the future for space is even better for the benefit of the population itself. So it's, for me, it's not just services or technology, but it's more making sure that the synergy is enhancing one path for the other for the benefit of the real end user, which is the us, yeah, the European community in global, that would understand better why we are using space for that.
Thank you, Valerie. Anthony, you don't have to confine your answer to European space sector. You can broaden it as you like. And also, even the word measure here can be interpreted in different ways. Perhaps it's a question of which quantity we should measure. Over to you, Anthony.
Yeah, thanks. I mean, maybe I'd give an Australian perspective. You know, the Australian Space Agency was formed 3 years ago, and before that, really, Australia had I would say, like a cottage space industry, and probably still does. But I think, you know, if you want to think about maybe if we think about measures to stimulate the space sector, which I think was the kind of thrust of the question, I think there's maybe three things. One would be creating the demand, and I think that's about having these kind of grand challenges, whether, you know, in the US context, sending people to Mars, but in the European context, I think Copernicus is a grand challenge. You know, it's a mission to planet Earth, and so having something like that also has a great connection back to societal outcomes is really important. And then I think, as Valerie said, having an environment, an industry environment that encourages innovation and allows you know, smaller companies to develop and inject their ideas. And then finally, I think maybe most importantly, because it's at the basis, is making sure that the education system produces STEM graduates, science, technology, engineering, maths, and that there are some space-focused degrees and postgraduate programs out there that people can sign up to, because you can have all of the industry stimulus you like, but if you don't have the people to actually populate the space agencies and develop the new technologies and work on the science, then you won't get very far. Thanks.
Thank you, Anthony, for a little bit of Australian perspective. It's been part of the answer. Carlo, please.
Well, it's difficult to disagree with anything that has been said by the previous people on the panel. But maybe just to enrich the discussion, I think the key is really to get the right balance between the technology push and the user requirements somehow. And it's not obvious, because we need a technology push. We need to ensure that we develop innovative solutions that don't yet have a user requirement. But it's also vital that we listen to the user and we respond to what the user are asking for. And in that sense, I think Copernicus is a force for good there, because as you mentioned yourself, Eric, in your introduction, there is a systematic analysis, collection analysis of user requirement done by Copernicus, and this can really be used to propel this innovation and ensure that future missions are truly user-driven. So, yeah, I think we are all on the same page here.
Okay, thank you, Carlo. There was also a panel question I think that you can address quite quickly. Carlo, I think this is only to you because it may refer to one of your slides. There was a question about a red line against the year 1979. Someone spotted with eagle eye. What's the significance of the year 1979?
Well, I guess it's as any year is a bit of a threshold, if you want. We use it as a standard year of beginning of the satellite era in meteorology, because it's the year that the microwave sounding unit was launched on Tyrus, and this was the first time we were really able to have a good profiling, if you want, of the atmosphere in the microwave and in infrared, which is vital for weather prediction. So it really marks a before and an after in satellite meteorology and in numerical weather prediction.
Great. Okay, that had a clear answer. I think if you don't mind, three panelists, if you can prepare in your head a 30-second or a minute max closing remark or comment from yourselves. We'll go to that in a minute. And before closing the session, which I will do obviously after those comments, I want to also relay to you as panelists that we've got some positive feedback from participants on Slido, and thanks for those. Thanks very much for those. So my own closing remark, just a couple of seconds, was that I wanted to respond a little bit to one of the questions on Slido about where does Europe stand compared to China, Russia, US. And I think when it comes to trying to combat climate change and saving the world, if you like, saving the Earth, it's not a competition, fortunately. And we're in a position where we are benefiting a lot from each other's investments. And there's quite a good, generally speaking, exchange of both knowledge and data. And I think that benefits us all. And I think it's therefore great, particularly therefore welcome that the European data policy is free and open, because that serves as an incentive for also other agencies to share data openly with us and others. Right, who wants to go first? Anthony, a quick closing remark from you and each of the panelists, please.
Thanks, Eric. Maybe just following on from your last remark. From a meteorological and climate observation perspective, I mean, Europe is a massive player, and if we think about the kind of the polar orbiting systems, then we have the US with its polar orbiting system, and then we have EUMETSAT with MEDOP and the follow-ons to MEDOP, and then we have China with the FINUM. So there's a kind of equality there, if you like, and I think Europe is equally as big a player as those other two, and certainly a leader in some of the technologies. I guess my reflection today is I think it's been interesting. We've had three quite different presentations, but my observation is that I've hopefully tried to give a global perspective of the value chain, and then you had Carlo talking about one kind of element of the value chain, maybe a kind of data user's perspective and producing products, and then from Valerie we had a mission focused. So for me that's great, because we've got requirements for climate observations feeding into Carlo's work, and then also feeding into the requirements for the satellite missions. So I think it's a nice kind of circle of presentations. So thanks, Ode, and thanks very much for the opportunity to participate.
Great, thank you. Valerie, please, equally brief.
Yes, for me, what it's exactly on the same idea than what just have been said. It's Copernicus is exactly that. It's connecting. It's really connecting all domains. It's there for connecting the users, for connecting the technical and the specificity of what is behind satellites, and it's also connecting the political domain. So I think it's what is probably making a huge change compared to the past, where you have this collective approach, much more organized than it was in the past. And Copernicus for that is a super good example. I think there is only good result that is coming out, and it's really paving the road for this dedicated type of mission, which are relevant for all human on Earth. So it's not just a European approach, but is something that is paving the global view for everyone in the future. So I was very happy to participate to this session and sharing this with the colleagues around the panel. Thank you very much.
Thank you, Valerie. Carlo, 30 seconds.
Yes. Well, first of all, thank you. It's been great to be part of the panel. So I enjoyed the discussion. I very much agree with Anthony. The different talks were complementary to one another. For me, there are two key messages to take away. One is that I think Europe is doing all right on space, and in particular, I would like to highlight, as you've done yourself, the importance of the open data policy. So that's really critical. And the element is really the STEM that you referred to, and the fact that we need to invest in people to increase the expertise. And is supporting on both these fundamental directions. So I'm very glad to be here and have presented what we have done. Thank you.
All right, thank you. So it remains for me to round this up and close the session. So thanks to Andrea for setting up this session and giving us the opportunity to form this panel and provide the presentations. Thank you to the panelists. Thank you to the participants, especially those that interacted with us through the Slido chats. Those were excellent, and as you see, those fed into the discussion that we've just had. So with that, I wish to close the session and remind you all that the next session in this Connect University will start this afternoon at 2 p.m. Another 2-hour session, with the title Digital Solutions for Climate Change Mitigation and Adaptation of Cities and Communities. So with that, I close the session, and thanks.
Thank you. Thanks to all of you. And also just a quick reminder for the speakers who have not sent yet the presentation yet, because we've received also questions about the materials. So if you can send us the presentation in PDF version, we can upload it on the website.